Hey, this is Mr. Ayton. This is the final video for pre-AP Chemistry. This is the final unit, Unit 15, Electrochemistry, Week 33. Again, this is it. This is all the bag of peanuts and shebang that you got. It is Week 33, and we're going to be taking a look at galvanic and voltaic cells, the cell potential and free energy. Let's get free energy again. We're going to be taking a look at half reactions and diagramming a galvanic cell. So what is electrochemistry? Electrochemistry is all about batteries, basically. It's all about, through a chemical reaction, we're converting chemical energy into electrical energy. This happens in every car, it happens in every battery, it happens in every... We're taking chemical energy and converting it into electrical energy, which means the E, which we call the standard cell potential, the E is called a standard cell potential, and that's measured in volts, is positive for something that is favorable. It's gonna happen. It's gonna work. You won't need to jack it with any electricity for it to work. It just works, which means your delta G, your Gibbs free energy, is negative, which means this is going to be favorable. So keep in mind, when the E is positive, the delta G is negative, and we call that a voltaic cell or a battery or a galvanic cell, okay? So let's take a look at these two reactions. We have a reaction which, these are two what we call half reactions, two half reactions. We have a copper reaction, copper plus 2 electrons gives you copper solid, and that's positive 0.34 volts. Aluminum plus 3 electrons gives you aluminum solid, that's negative 1.66, okay? Now, we want the E to be positive in order to be a favorable chemical reaction, which means the delta G will end up becoming negative, okay? So we want the E, the standard cell potential, to be positive. Now, in every battery, you have what's called oxidation going on, which is losing electrons. Losing electrons is oxidation. Leo the lion, right? Gaining electrons is reduction. Gaining electrons is reduction. Leo the lion goes grrr, grrr. And the oxidation occurs at the anode. So anox. At the anode, oxidation is occurring. Reduction occurs at the cathode, which means anox and a red cat. Okay, so Leo the lion goes grr, and anox and red cat, and those will very much help you out. Which means you can see both of these half reactions, they're both gaining electrons. Copper plus 2 electrons. Aluminum plus 3 electrons. They're both reduction half reactions, which means I'm going to have to flip one reaction. The reaction that I flip is going to be the oxidation reaction. So the reaction that I flip is going to be the oxidation reaction. So I need to flip the most negative because I want my E to be positive. So we're going to flip this reaction right here. So when we flip this reaction, the aluminum solid comes on this side. The aluminum plus 3 electrons comes on that side, and that becomes positive 1.66 volts, okay? Positive 1.66 volts. So we flip this second reaction, okay? I'm trying to cross my way through that. And it becomes positive 1.66 volts. Now, something I have to do, now the reaction that I flipped was my oxidation reaction because you see how we're losing electrons. Electrons are being lost, which means this is occurring at the anode. So the reaction that I flip is at the anode. The reaction that I didn't flip is the reduction reaction because it's gaining electrons, which means this is occurring at the cathode. And this is positive 0.34 volts, okay? Now, something I got to do before I add up my two reactions is I have to balance my number of electrons. Can you see I have 2 electrons here and 3 electrons here? So what's the common multiple between 2 and 3 is 6, isn't it? So I have to triple this, which makes this 6, which makes that 3. But we don't triple this. It's not like Hess's law. We don't triple this because this doesn't say volts per mole. It just says volts. So we don't triple it. Now we want to make this into 6 electrons. So what are we going to have to multiply 3 by to make it 6? Is 2. So 2, 2, and that makes this 6 electrons. So we're transferring 6 electrons in this reaction right here. So what's happening in this reaction? We have 3 copper ions, which are aqueous, plus 2 aluminum solids. And what are we making on this side is 2 aluminum plus 3 aqueuses plus 3 copper solids. And I'm going to add these two things together. This 1.66 plus 0.34, and that gives me a voltage of positive 2.00 volts. And that's my standard cell potential. Remember, when your standard cell potential is positive, it's a favorable reaction. And take a look. Look at my overall reaction. I have 3 copper atoms, makes 3 copper atoms. 2 aluminum atoms makes 2 aluminum atoms. Look at the charges. 3 and plus 3 times plus 2 is plus 6. 0. This guy is 0, isn't it? Okay. 2 times plus 3 is 6. 0. Do you see how both atoms and charges are conserved? And how many electrons were transferred? 6 electrons were transferred. And those 6 electrons, as electrons get transferred, that means current or amps, I, right? Current is going to be moving, which creates the electricity. And so that is the half reactions. So let's take a look at this in terms of diagramming an entire reaction. Diagram an entire reaction. And I'm going to move this a little bit this way. That way we can all see this. Okay. And let's take a look at which reaction. Now, we want a favorable reaction. So which reaction are we going to flip? Are we going to flip the copper reaction or the tin reaction? We're going to flip the tin reaction, aren't we? So the reaction that we flip, this one here that we flip, and I'm going to do everything here in blue for the flipping. So we flip this reaction, which means this is my oxidation reaction. It's occurring at the anode. And this flips it to become tin solid, breaking down into tin plus 2 electrons. And that makes this positive 0.14 volts, doesn't it? Okay. So I'm going to flip the most negative, so that flipped this reaction. Now the reaction that I'm going to keep is this reaction up here. And the reaction that I keep is the reduction reaction that's happening at the cathode. Okay. And before I go adding these two reactions together to get my overall reaction, I need to balance the electrons. 2 electrons are being added on this reaction. 2 electrons are being released on this reaction, which means I'm already balanced, which means I can just add up. Everything on my reactant side, I have copper plus 2 plus tin solid is going to make tin plus 2 plus copper solid. And I'm going to add up 0.34 plus 0.14, and that gives me an overall E for this reaction of positive 0.448 volts, okay, which means since my E is positive, I know my delta G is negative, my Gibbs free energy is negative, which means this reaction will happen. It's going to produce a voltage, and it's going to produce positive 0.48 volts on this voltmeter when this switch is closed. Once this switch is closed and we got current running through it, that's what's going to happen. So let's diagram what's actually going to happen here. Let's start with my reduction side, which is the copper electrode. So this is copper solid right here. This is copper solid, a copper electrode, okay? And you know what copper looks like? Copper is kind of a brown color, okay? So we have a copper electrode right here. Copper electrode made up of a bunch of atoms. I'm going to change this to just a bunch of copper atoms, aren't I? Okay? Because I like particle diagrams better. So here's all my copper atoms, okay? And this is in a copper solution. Okay, a copper solution, and I have a bunch of copper plus 2, copper plus 2, copper plus 2, a bunch of copper solution. And we know copper is a blue solution here, a blue solution, okay? And this is occurring, this is the reduction side, and this is occurring at the cathode. So this is the cathode electrode here, the cathode electrode, okay? So let's take a look at what's happening to the copper. The copper is going from plus 2 to copper solid. So every single little bit of time, we're losing some of this copper plus 2, which means we're losing some of that blue. And we're making a little bit of solid. So you can see how a little bit more solid is coming on here. And then guess what we do? We lose another copper plus 2, which means this is becoming less and less blue. And we're making more copper solid. What's happening to this copper electrode? It's increasing in mass, isn't it? The copper electrode is increasing in mass. Now, it's not getting mass from nowhere. It's not creating mass. It's the mass from the copper plus 2 in the solution is becoming copper solid, copper atoms, okay, solid. And so you can see the electrode looks like it's gaining mass. We call that plating. It's plating that copper solid. Now, let's take a look at what's happening on the other side. The other side is the anode, isn't it? The anode, which is the oxidation side. And here we have tin. Tin is silver, so the best silver I'm going to do is this tin atoms. So I have a bunch of tin atoms here. And this is in a solution of tin plus 2. Okay, this clear solution of tin plus 2, tin plus 2, tin plus 2, tin plus 2. I'm going to do this very, very similar. Okay. Now, what's happening to the tin is, see how the tin solid is becoming tin plus 2. So this tin solid, I hope you can see, we're losing some of this solid here. We're losing some of this solid. And it's becoming tin plus 2. So we're losing, this electrode is actually losing mass. We're losing mass, aren't we, to this electrode? And it's becoming tin plus 2. Tin plus 2 aqueous. It's dissolving. So whereas the copper's making more solid on this electrode, the tin is actually decreasing in mass on this electrode. And think about what's happening here. That when the tin does this, it's losing electrons, isn't it? It's losing 2 electrons. So it's losing 2 electrons. And those electrons are moving over here as the copper is gaining those 2 electrons. Because gaining electrons is reduction. So the electrons are moving from anode to cathode. And just keep in mind, the electrons always move this way from anode to cathode. And as the electrons move, it's producing a voltage of 0.48 volts of electricity as it keeps moving over and over and over again. Now, I have to have a full circuit, which means I have to have this thing called a salt bridge. This salt bridge helps to keep the current flowing, but it also helps to keep electrical neutrality, okay? And we're always going to use spectator ions for the salt bridge, which means alkali metal ions like potassium ions, sodium ions, lithium ions, they're really good, and nitrate ions. Spectator ions, so spectator ions won't damage or take any of these moles from my reaction. Now think about it. As this is gaining 2 electrons, gaining negatives, you're going to need positives coming this way. Remember these copper plus 2s? They're getting lost, aren't they? Which means we have to replace this with a bunch of K pluses. So all the K plus starts migrating this way to keep electrical neutrality. Well, this one is losing negatives, losing electrons. It's gaining a bunch of positive tin plus 2s. So what do we need migrating this way to keep electrical neutrality? Some of those nitrate ions, some of those negative ions are migrating this way. And the salt bridge is keeping electrical neutrality. And that is what's happening in a galvanic cell. And we just diagrammed an entire galvanic cell. So, hope this made sense. This was Unit 15 Electrochemistry. That's the last thing we're going to learn this year in pre-AP Chemistry. This is Mr. Ayton, signing off.